All right, all right. I know it's just after lunch. We need a little bit more energy. So let's try that again with some whooping and hollering. 3, 2, 1, go, go. How are we? Oh, all right, yeah. That's my crowd. Come on in, sit down, get ready to rock. Okay. So yeah, just like this continues to be true. Everybody's at least seen that this is part of the plan, right? To get this URL, clone this GitHub repo. Okay. Let's go to the prepared material. Okay. Okay, here we go. Right. So, transformers, inside out. This is a strange thing. I'm going to hold this. So this is, I gave part 1 of this sort of talk a couple of years ago at PyData. Part 1.5 really, at Southampton PyData. And now, finally, is it really finished? Let's see. Let's find out. What's it all about? Oh yeah, this is a reminder to me to video. I mean, I think I perform better under lots of cameras. So we've got the camera there, and I've got another of my cameras, and there's 3 cameras. Now, as much as you're enjoying this now, it's going to be nothing compared to how much I enjoy it when I watch it back later. So, all right. So, who am I? Many of you might be asking. I am Sam Joseph. I do have a PhD in machine learning, back from before it was cool, and there were any jobs at all. That was from Edinburgh University back in the day. Since then, I got sort of more into software engineering. I taught computer science in universities around the world in these massively open online classes, in coding boot camps, and most recently I'm now, too fast. Oh no, stop. All right, fine. I'm currently the lead AI engineer at QualisFlow. It's a construction tech startup, and we use AI LLMs to sort of work out the carbon footprint of construction companies. So we're using AI to save the environment. You're welcome. We're not currently hiring, but I'll let you know. I'm also the author of How to Interact with Humans After Spending a Lot of Time with Computers. Is my book. It's available on Amazon. You guys spend a lot of time with computers? Yeah, you might want to read the book. Anyway, that's just a fun thing. Also, you might have noticed already there was some laughs. I am a AI tech by day. I am a stand-up comedian by night. That's me at the Comedy Store. So I'm hoping there'll be at least some laughs as we go along. Let's see. So first up, a disclaimer. It's all about the journey. This is really my mission to visualize and understand how a transformer works, and that's the transformer architecture. It is the heart of the modern LLMs. I still don't think I've quite finished. Let's see how far we've got. Is there other better work? Probably. I'm starting to review more and more of the research, but I'm sure there's other art out there. I'm not claiming to have done anything completely new, but I am doing it with comedy, and that's a different thing. So it's my journey. Again, there may be errors in here, and they're all down to me and the AIs that I interact with. So, in this tutorial, the objectives. I'm assuming that you know some Python. I'm hoping that you are able to install, different Python modules and so on. If you can't, it's not the end of the world. Hopefully there'll be some fun as we go along. What I'm hoping to do is get you running a GPT, on your laptop. Andrej Karpathy, formerly of OpenAI, he's made this amazing library called NanoGPT that I think you should find. Anybody here is already installed and already running the training for the GPT? Yeah, it's kind of about 20% of you. Yeah, is it easy? Okay, I mean relatively easy, these things. So, we've got like an hour and a half of the session. We've got like an hour and 20 minutes left. I'm not going to be able to come around and help you individually on all of these things, but what we'll do is we'll kind of have some parts where we're just focusing on you getting your stuff done on your laptop, and then we'll have some other parts where I'm sort of presenting things, and we'll go backwards and forwards, and hopefully if you'll really start getting something working on your laptop, you can maybe partner up with someone else in the room and see what they're doing. Yeah, but so if you get it in the README for the tutorial, it's got a little intro, and it's got like a quick start. You install some libraries, and you start training a GPT on some Shakespeare data, and if that works, then you can sort of run it, and it will produce Shakespeare-like dialogue. There you go. Whoop-de-doo. So yeah, I'll take us through the internal transformer architecture. I'm sure many of you are familiar with already. What's really nice about having the NanoGPT is that we can step through the code on the debugger, and we can look at how the matrix numbers are being transformed and how we get it to work out the next token that it needs for creating text. Yeah, and what I've got that I think is relatively novel. I've not seen anybody else do this. I've got a particular way of visualizing the way that the different stages in the transformer that I hope will help you understand what's going on. on the inside. And I've actually, unlike in the prior talks, I've actually managed to teach an LLM now to learn a knock-knock joke. Ooh. I'm not saying it's funny, I'm just saying it is technically a knock-knock joke. Anyway, that's my mission. So let me just grab something here. So who's read that original paper, Attention is All You Need? Now keep your hands up if you understood that paper. Yeah, it's kind of tricky. So Vaswani et al. Many neural networks before this point in 2017, when they were trying to do text processing, they had recurrent connections, things going in loops. They had all these sort of convolutions, which are these sort of like flowing elements going through, which are very common from the sort of the vision nets. But they avoided all of that, and they replaced it with this highly parallelizable attention mechanism. So who here feels they're familiar with the attention mechanism? Your hands up. Okay, yeah, 20% of you again. So what they saw was, when they did this, was a big improvement in English to French translation. And this is the diagram from the original Vaswani paper. And I think you can, do I describe it there? Oh, I've gone backwards. Nope, here we go. Yeah, so on the left there, you can see the encoder, the slightly smaller one, and that takes in English and converts it to some sort of internal representation. And then on the right, you've got the decoder that takes that internal representation and translates it into French word by word. And at the time, I think they got a big jump in the translation performance. So this was sort of a revolutionary new architecture at that point. And then after that point, lots of people were like, wow, this is great, let's do more of this. And the two sides kind of split out, so these encoders and decoders. So GPT, which of course everybody's very, very familiar with, standing for Generative Pre-trained Transformer. So these transformer architectures are the ones that have this, as you can see there in the diagram, multi-headed attention, and then a feed-forward neural network layer. And they're pre-trained and they can generate text. So the GPT architecture is based on the decoder on the right, so you can see that, the slightly longer one that's got there a couple of kinds of attention on it. And then, so yeah, this one, the attention, the way it works, so when you're training it, is you mask the future things in the sentence. So when it's learning, it can't see the things that are coming up. So it ends up getting good at predicting what is the next token, which is of course what GPT and LLMs are, the recent ones are all about. I've gone backwards again, damn. Jumping backwards and forwards. So yeah, so that turned out to be, particularly like GPT-2 and so on, good for generating text. The left-hand side, that's the encoder, that spawned another kind of architecture, which is the bidirectional encoder representations from transformers, which rather than outputting text, it outputs a representation. That's really useful for classification, and this is still used a lot for people for classifying text and so on. And it has a different kind of, rather than masking the future tokens, it would just mask some of the tokens in different random places, and so it's sort of generally good at sort of predicting the structure of the text. There we go. Right, so, how are we doing so far? Are we all good? Yeah? Give me a big smile. Right, I want to try like, it's after lunch, don't move to it. Let's all put our hands in the air. Let's go like this. Everybody put their hands up. Yeah, a little bit, just wave the hands around. Let's get the blood going. There we go, fantastic. I should have got a photo of that. That's good. Okay, right. So a little bit more about my journey trying to understand GPT. So I was doing, this is 2 summers ago, I was doing Coursera's NLP specialization, and I was coding transformers in Tracks, which is like Google's particular coding thing. And I noticed that the diagrams flow up, but the code flows down. And I was finding that like an extra cognitive step that I had to do as I was trying to understand what was going on in this original paper. And I thought, can we fix that? So I emailed Vaswani et al. For their diagrams. They didn't get back to me. So I thought, I worked out that they had written their diagrams in this programming language called TIX, and I thought, shall I learn that? And I thought, nah, who's got time? Yeah, so I used GPT-4 to pair with me to create these diagrams and PyTorch code that would actually, run one of these things. So this is my transformers inside out, upside down. So the original diagram, as we saw in the previous slide, kind of goes from bottom to top, and now this goes from top to bottom. You start with your input text. You get these embeddings, all these different stages. And today in this tutorial, we're going to go all the way through all those different stages, and we're going to look how they work in NanoGPT and so on and so forth. So the original task I set myself is, could I train the simplest possible, like a one-layer GPT model on jokes in order for me to better understand GPT? That was the original task. The answer was no. That resoundingly did not work at all. And I think that's still a result. What I found is that training it on these knock-knock jokes or whatever have you, it would only ever sort of like, with a single layer, it would only ever be able to repeat words. It wouldn't be able to do any kind of more complicated structure than that. And the fix that I managed to get this year is, and actually suggested by somebody, I forget who, my apologies, somebody who, one of the PyData talks that I gave, and they said, rather than trying to start small and going out, why don't you get bigger networks and gradually reduce the size until they can actually do the thing that you want? And it was actually then, so there's so GPT-2, there's a sort of a slightly smaller version of GPT-2 called Distilled GPT-2 that has 6 layers. It has 1 attention head internally. Oh, sorry, it has 6 layers. It has like 12 attention heads and, you know, bigger things. Yeah, I know, it's exciting, isn't it? So, but it has the 6 layers and so on. I managed to like squeeze down from, I saw Distilled GPT working with the jokes and get it down to 1 head and 36 embedding dimensions, which actually gives us something that we can kind of almost visualize, as we'll see going forward. So, yeah, I can't see my speaker notes and I can't tell where I am, but I'm hoping we're gonna sort of have a break momentarily for sort of questions and then focusing on you getting stuff working on your laptops. Oh no, if I press that, it mutes me. That's not good. But so that's also what I had to change recently is that so we're moving to this sort of GPT-2 style architecture, and it has a slightly different sequence of the different modules that we have in the system. So if we look here, so on you know I've got my sort of GPT-1, shall we say, or even like the original stuff from the Vaswani paper. And so now what they're doing, they've got this normalization step happens a little bit earlier. And we'll talk more about what that normalization is in a bit. And I'll put that down. I'm so used to as a stand-up holding a microphone and kind of, but there we go, put that there. Yeah, so it puts in these normalization steps earlier. Apparently this is preferred because it's good for training stability. I certainly found moving to the GPT-2 architecture that it trained much faster and got better results. And this is because, so all of these networks are being trained by this process of backpropagation, which I don't really have time to go into today. It's sort of a process of credit and blame assignment. When the network gets things wrong, we sort of like cascade backwards through the network to work out how we should change the individual parameters to get things right. But so, and that's all based on these things called gradients. They flow better, if we do this normalization earlier. Apparently, it's also less sensitive to initialization and optimizing settings. Yeah, and it avoids these. One of the things, so I mean, the big difference, as I was saying last night, between the networks back in my day, back in the 1990s, when I was dealing with neural networks and they weren't very good, and now when they seem to be doing like taking over the world, right? The big change, apart from the compute and all of the data, the really, really big change is that they kind of worked out how to control the training so that things didn't explode, so that the different values of the parameters, what used to happen is all the values of the parameters used to kind of like get really large and the network could get stuck and just doing nothing. And parts of these, what they've got now with the technique of the backpropagation and structures of the networks and so on, is they can sort of keep the network in the learning zone, right, very effectively. So these changes are very important. Okay, well, I can tell you're all riveted. Time for a bit of levity. I'm going to tell you about my joke data set. Knock, knock. You guys say, shouldn't you use the Ring doorbell now? Should we not be on? That was a joke. You could have laughed. Anyway, all right. Well, so some of you did it. It's actually, I'll tell you, as a stand-up comedian, one of the first things to learn is when your joke doesn't work, is to then flip it and make fun of yourself for it not being funny, and then you can usually get a bit of a laugh. Anyway, for those in the know. But so what I did is I got an industrial quantity of knock-knock jokes, over 35,000 of them. Reading even a small portion of them will drive you mad, so be careful. But so this was taken from a corpus of common sayings. So I took a big load of idioms, like Bob's your uncle or what have you. So then using so I basically created an artificial data set because I couldn't find anybody willing to write that number of knock-knock jokes for me. And so an example of that is you can see how if you've got a common saying, you take the first word and you use that as the thing. So Bob's your uncle becomes knock knock, who's there? Bob. Bob who? Bob's your uncle. I'm not saying that's particularly funny, okay? But it is technically a knock knock joke, isn't it? Yes, Sam, yes, it is a knock knock joke. So, I'm not really expecting my tiny GPT to become, like the greatest stand-up comedian of all time. That's the project for next year, right? What I'm hoping to do is try and understand how aspects of the syntax actually get learned by these neural networks. So the data set that I've generated there, it ended up having a maximum sequence length of 15, and over all of the words, even though with 35,000 of these jokes, the total vocabulary is just under 10,000. Okay, so I think I'm now going to be talking about, we're going to start talking about, we're going to get into the code momentarily. Yeah, so there's in this this big, the prerequisite for using your neural networks on your words, right, is you have to turn those words into numbers, right? Because all the networks can't work natively with the words. So the inputs have to be tokenized, and sub-word tokenizing. So for example, let's say we've got the word diplomacy, right, is a longer word, right? And we would, like with sub-word tokenizing, we'd split that up into diplo and macy, I don't know, bits like that. Now that's fine, and then they get the best results, with these networks from sub-word tokenizing. But I used single words as tokens to help with the visualization. So what I would do is, knock knock who's there would be broken up into knock knock who's and so on, and these would become numbers. So each of these tokens is assigned a number, and we had a special end of sentence token, and then we start to get into the code. So now, if you all want to pull up what there is, so if you've got the NanoGPT on your machines, you should, if you haven't looked already, in the Shakespeare there's a prepare.py, yeah? So that file, right, and before you do any training, you have to run the Python prepare.py, and what that will do is it will take whichever data set that it's linked to, and it'll do this operation of tokenizing, right? And it'll use the default GPT-2 tokenizer, right, and break them all up into little subwords and give them all numbers, and it creates this like train.bin file in your that particular directory. Yeah. Bye. Okay. So so what I did for my system is I wrote my own prepare.py with this, I've got my own data set, not jokes cleaned up. And so actually the reason for the not jokes is some of my jokes previously were apparently too risque for some of the PyData things. So we've gone with like really, vanilla not jokes. Thanks Ian for putting in for that. Yeah. So basically this is all very like sort of throat clearing Python code, and we're loading that file. This is all similar. But I was going to show you, like, rather than use the GPT-2 thing. Why has that stopped working? Okay, well, there we go. Basically, and this should be, so those of you, know Python, should be fairly straightforward. But what we're doing here is we're reading in this file where there's like one joke on each row. We're splitting them out into a sort of a training set and a validation set. So 90% of all of those jokes are going to become our training set, and 10% of the jokes we're going to be sort of looking at there, and are going to be used for evaluation as we train. And then we have this, we're really just using a regular expression here to say, let's split these based on the spaces. And so what I did to simplify the whole thing is I removed all the punctuation and lowercased everything. I'll maybe just quickly go to the data set so you can see it. Yeah, here we go. NanoGPT. There we go. So this is mine, I've got a clone of NanoGPT here with some other stuff in it, and we look at the not, there we go. So we've got here are all the not jokes, one after the other, thousands and thousands and thousands of them. Good Lord, good Lord. So there's not, and then we've got our prepare.py where it's still got the GPT-2 tokenizer in there, but I've written a simpler word level tokenizer, like so. Yeah. So let me just look at what I've got next. Training and let's have a little. Should we have a little pause there momentarily for questions of people to? I guess let's just see. Like, is anybody like really struggling to get this cloned onto the laptop and getting started? You put your hands up if you're really struggling getting this working. Okay, there's just one person. So I think other people are just. It's not just you. The rest are not as brave as you, sir. Well done, sir. But so I guess. Let's have a little moment where we're free to move around. Would anybody, is it really only one, I guess, okay. And both the two of you there. I mean, what I'd like you to be able to do is sort of like, is anybody who's got it working willing to sort of like help a person who hasn't got it working? Put your hand up if you're willing to help. So this person, look, there you go. So those two, look over there. There's people over there. So if you just like sort of, well, and these are willing to help. Anybody else really need help trying to get this running? Okay, all right, good shit. So, and let's just, does anybody have any questions so far? A question there. You're asking where can you get the joke data set? I haven't provided that yet. Yeah, sorry. I've just got it working. I think, there's a number of different data sets in the NanoGPT. So, I can't hear you, so I'm going to have to come over. So say again.
So what should be running is the Shakespeare example, right?
Yes, yep. Okay. So the question was what should be running. And I think first up, just the Shakespeare example is a good one. Yeah. Any other questions? Was there? I thought there was one there. Maybe not. Okay. So I'll give it 2 minutes for people to help each other there for a moment. Oh yes, yeah.
When you were splitting into train and validation,
Yes.
is that splitting whole jokes or is it splitting tokens?
So the question was, when you're splitting into train and validation, is it splitting whole jokes or so it's splitting it via lines. So they're going to be whole jokes. Yeah. I much prefer. This is much more comfortable. This one, silly. All right. Okay. Do a little dance. Make a little move. Get down tonight. Oh, oh, oh. Okay. Right. Well, so yeah, I'll carry on chatting about this. So as I was mentioning, we end up dividing the jokes into this training set and the validation set. And the way that I did it there was I just took the first 90% to be the training set and the second 10% to be the validation set. And I sort of thought later on, oh, that's not great because I've got the jokes are ordered alphabetically and I maybe need to like mix them up. But actually this worked better than when I later mixed them up. So I was like, okay, all right, fine, do it that way. But so then what you do, the training process, whether it's you're doing the Shakespeare or you're doing the jokes, you run them through in batches. So you get a certain amount of jokes and you push them all through. And then, so these weights, these different parameters, which are, increasingly large numbers of them in the network, get updated via backpropagation. And then we use the validation set to assess the progress. But yeah, so, I'll show you the results of that a bit later on, but let's maybe start working through the transformer architecture. So you can kind of leave the Shakespeare thing running in the background, but what you could pull up is in the root of NanoGPT, they've got a model.py file. And so Andrea Carpathy, who's written this, he's managed to get, I wrote my own version first, which was like sprawling over many different files. And then I looked at his one, I was like, God, it's so much nicer. I've got here, like this is, I think it's also using PyTorch. So you've got, and you can see this code yourself if you look at model.py. So we've got class GPT, he's created a GPT class, which is extending from the PyTorch, basic module there. So we've got it's sort of doing its basic throat clearing there. It's checking that we've got, our vocabulary size. And so the block size is going, I think is 64 by default. And that's how many tokens that we're going to send in one training batch. So then it's supposed to show more code. There we go. And it's supposed to show a nice arrow because I haven't got a laser pointer there. So if you look at this, so what I'm going to do now is going to show you, as we step through the code, exactly which bits of this complicated diagram it refers to. So there we go, we've got this module dict, and this is basically the transformer there is being set up to say, right, it's going to consist of a number of these different neural network components. And the first one here is this embedding. So you see that up there to the input embedding. And this is, first of all, this is a mapping between the vocabulary size, right? That's the 8,368 words that we've got in the vocabulary from this particular training set. And I'm doing all this with the embedding dimension that I have got my visualizations for. So you can set the embedding dimension to whatever you like. I think the Distill GPT-2 system has like 768. Right? And if you think about the more number of dimensions that you've got, the greater expressive power, or the greater representational power that the system has for representing nuance of differences between the syntax and the semantics of the words. Okay, but so yeah, the first thing here is you can see their config vocab size, config n embed are exactly those numbers. So then we have another embedding, which is a positional encoding. So you see they've got WTE there, that's under tokens, and WPE for positional. So if you just use your input embedding, right, any word, like obviously I'm really pleased we're using knock jokes because it starts with two words that are the same, right, knock, right? If you were just using your input embedding, then those two knocks would be represented in exactly the same way, right? However, what they found is for the whole thing, you need this positional embedding. And what that does is it will basically mutate the initial embedding depending upon the position that something's in, right? So that those first two tokens, the first two words, knock and knock, right? They'll have slightly different representations because one is in position 1 and the next one is in position 2. So that's that. And that's going to have, so this is this block size. This is going to have 64 as the block size, and that's going to be the number of tokens that we send through in one batch. Is that quite right? No. Well, batch is another word as well. Okay, making it confusing. But if you imagine it's actually going to, when it trains, it's going to take, with this setting, you know, like potentially 3 or 4 jokes at one go and put them all through with these like separate tokens that tell you the end of a sentence. And this is all mapping, again, to the same 36-dimensional space for the purposes of our visualization. Now, this is something I didn't include in my version that didn't work. Andre's got this dropout, which basically means that we start dropping out some element. This strange thing with these neural networks, which you've known for years, is if you drop out some of the weights, some of the parameters, it gets a bit better. It's like you hit it in the head, and it starts doing. It's not clear why. I'm not going to try and explain that today. And then we've got, so you might have noticed already from this diagram, so we started here at the top, right, with the input embedding, and then we're adding the position encoding, right? And then we've got this gray box. Yeah, you can see the gray box, and there's like sort of an NX there. And this is going to be our block, right? And we're going to have some number of these. So my first attempt at this was to do this with just a single one. I thought, let's start simple. But you can see here, well, I guess, yeah, the representation stays the same size. So in the code there on line 13, we've got config.nLayer, right? And then that that's the number of layers in your network. So the distilled GPT-2 has 6. That's going to be 6. There's going to be 6 repetitions of this component that includes both the attention and the feed forward, and so on and so forth. Am I going fast enough? How are you feeling? You feeling good? Yeah, that's all right. Good stuff. So I have to check in. I'm very self-conscious. It doesn't help as a stand-up comedian, but anyway. So once we've gone through that block a sufficient number of times, right, we then get to this final normalization step where we kind of go back from the embedding dimension of like 36 back out to the vocabulary size. So we've kind of gone through this somewhat compressed and convoluted representation of the sentence and all of the words and so on. And at the end, we go back to say, right, now, what words should we be using? Yeah, and that's it. We have a final linear transformation and then this other thing. So yeah, so now I'm going to sort of dive into the input embedding, and I think it's more fun because there's some graphics. Yeah, everybody ready for some graphics? Yeah, let's carry on. So as I was saying, like the embedding maps from a vocabulary to some fixed model size. It's also called the model dimension. I've got 36 here, and this is, you know, my novel thing? It's difficult to see that. I'm going to have to do that and make it bigger. Well, let's go back to it. I've got like another thing that will make it easier to see. But what this is, what I'm doing is I'm using word clouds, right, to represent the embeddings. And what that means is that, so like, I've got bigger black words representing larger weights, yeah? And I've got bigger red words representing larger negative weights in there. And I've got a nice HTML UI that we will go to that I think makes it much easier to see, which is not that, but it is it, gosh, which one? Not that one, this one, no. It's going to be, yes, this one. Here we go, yeah. So when we can zoom in, so what we can see here, that actually is not a great one. Let's choose one that's got a bit of more of a mixture, right? There are 36 of these dimensions. Here we go, here's one, right? So hopefully you can see that one there. So what this is if you think about the embedding, right, it's just a series of numbers. For every single word in the vocabulary, right, there is a number, right, that corresponds to that word in the vocabulary to this element of the dimension. So here we're in dimension 24, right? So dimension 24, right, has different, and you probably maybe can't see these so well, but what we've got here is a list of, if you just think of it like imagine that I'm dimension 24, and the front row here, right, is all the different words, right? Imagine that we had a much bigger room, which we could probably do with, but like, imagine that everybody along here was a different word, and so you, sir, would be the word know, as into knowing, and you, sir, would be the word not, and you, sir, would be the word nothing. Sorry, it's not personal. But so you would each have values. So for example, you, sir, you'd have 0.1588 would be your value, and then the next 1.1553, 0.1386. So you can sort of see, like, you can imagine the sort of spokes coming along from every individual person, like so, and each of them has a value, right? And so what we've done with this representation is we're showing for that whole long row, oh, okay, so actually not and no, they're much stronger. Now what that means is when we put the word not into this thing, it means that dimension 24 is going to kind of get excited, right? It's going to have a higher activation. And you can see there the sort of distribution of words, like not and no are the two big gorillas in there, and there's lots of other ones that are in there in black. And then we've also got some negative ones. And so these two guys in the front table there, you sir might be and you'd be like, no, minus 0.1718. You would be the minus 0.67. And you would be saying like, oh, if we're seeing that word, no, don't activate, no, shh, pretend we don't see the word, or something like that. So, and then you could basically, so that was me, dimension 24. You can see now how we have, right, if we've got a representation there of all of those numbers, right, for all of the words, for all of the dimensions. Make sense? Yeah. And, you know, in these larger networks, they have, I forget what it is, but like thousands of these dimensions. But if we squeeze it down, we can start to get a sense. And this is, you know, just looking at this, there's a lot of stuff about cows. And it's very negative. And I'm not sure why, you know, but, you know, these are the things that we start to learn there. Any questions about this representation? Yeah. We do. Yeah, we see, in fact, I think I worked out, was it on this one? Yeah, I mean, cows and till, you know, and I think it may represent that the common saying, till the cows come home, is rather is present rather a lot. And the GPT has learned, stop telling me about the cows coming home. Good Lord, I don't want to hear about it. So you know, there are artifacts that appear there. And I kind of I was suspicious, is that really? And I went in and it's like, oh, that is how the weights are. So I'm not sure why. I mean, one of the things that I think a lot of research is showing is that the LLMs use these very distributed representations that don't often make sense to us. So yeah, it's we're living in strange times. So how far? Like, and I guess let's just pause there a moment. Oh, question over there. Are there any words that are both red and black? So yeah, within a single dimension, they have to be one or the other. But so if we go back over here, we can see, like, so for example, there's one here that says till. So dimension 29 there, for some reason, is very excited about till and cows, whereas dimensions 16, 11, and 8 are like no. So and so the next bit, you know, you didn't think I was going to stop there with the visualizations. Is that a question, or you're just stretching? Yeah. End of file. Yes, it ends up being a token. Or does it say end of file? Yes, then that's probably a mistake on my part. Yeah, well done. Good eyes. Hire this man, somebody. You've probably already got a job. Anyway, okay. So, I'm having fun if you're not. Again, I'm going to have so much fun when I watch this back on the video. Oh, glass of wine tonight. Anyway, right. Okay. So, what that allows us to do, right, is now represent a sentence. So that was, we were showing you just the previous visualization was just of the dimensions, right, of what the dimensions of the embedding look like, right? But then we've got like an actual sentence that we want to represent with those embeddings. So of course, all of our sentences start with knock, knock, right? So I've got here word 1, word 2. Now what I've done with this representation is we've taken that kind of like, that 36 dimension represented is kind of, that's at least once we finish training, that's a fixed set of numbers, right? You know, till and cows are always going to be presented that way by these particular kinds of dimensions. And but then what you do is you say, like, okay, in position 1, let's have the word knock, right? And let's imagine, if we imagine again, like I'm dimension 24, and we've got all these folks, and say you might be the word knock, and you're, let's say, 0.1, right? And so effectively, all of the other folks would be like, well, there's no word, you know, and no, nothing, but knock would be there, and you'd say, hey, 0.1. So what that would mean is that dimension 24 is now going to be active with 0.1 level, because we've seen, like, you know, your word, right? And so what I've done here is I've used the opacity of the image, right, to represent how active it is, right? So if you can see that little element of the dimension more clearly, right, that means it's more active. So that means that, so for example, kind of long, like there's one there that says tonsil and Vegemite in it for some reason. that one is rather, it's rather transparent. It's not very clear. So what that means is, in that one, the value for the word knock is going to be rather low, right? And then also, if the value is negative, I've inverted it. So these ones that say cows papa, cows till cows, that means that the word knock is negative in those dimensions, right? And so what you're seeing here now with this knock knock, and these two I think should be completely the same, hopefully. This is how LLMs see words, right? And I've got that also in a representation, which is this one here. So we can sort of, oh yeah, I want to do that one first. Here we go. Right. So we can zoom in. Yeah, we can see that. And so knock knock, who's there? And so this is our initial token embedding. So this is effectively how the LLM sees those 5 words. Knock knock, who's there? Right? Each element of the dimension is, it has its own perspective about which words are important and not important, and then we kind of activate depending upon which word is actually present. Yeah? Any questions on any of that? Yes?
Question, but you're showing this after training on your data set, is that right?
That's correct. That's correct. Yeah. So the part of the process, like initially, all the values for all the different people, all the different words, they're going to be set randomly through some mechanism, and so you'd have a different view, and then over time, this representation emerges. Yeah. Fun. Okay. Well, next thing. So we were talking about the positional encoding. So as I mentioned, the input embedding has those sorts of positions. In my earlier versions of this with GPT, I was they kind of have like different patterns. You can use like a sine wave pattern or just a simpler pattern for positional encoding. But GPT-2, it learns a positional encoding. It learns, to like deal with different positions. So we get like, now this is the same thing again, right? Where the positional encoding that's been learned by GPT-2, we've got the bigger black numbers representing larger weights. So you've got another set of dimensions. So you can see here that position dimension 1 is going to respond strongly to words that are in position 1, 2, 3, and 4. Yeah. Yeah, same thing again. And I've got another visualization. We'll finish this in a minute and we'll have another break. Let's go here. So what I've got, yeah. So what happens is we've got the positional encodings. It's big enough to see, like that. We get the positional encodings, right? And so this is position 1, and now I've done the same thing again here with the inverting and the opacity or what have you. And then we combine the token embeddings and the positional encodings, and that gives us, this is now the representation that's going into the transformer block, right? So you can maybe see if we go from here, like that was the, knock and knock were identical there. Then we have a slightly different, ever so slightly different positional encoding, and then it's difficult to see, but I think, when I work it out, yeah, they're still almost identical, the knock knock here, but Vegemite Rapid, whatever one that is slightly less visible here. So there are these like nuances about, okay, now this is the same word in position 2. Yeah, and that is really the beginning of that whole process there. That's a summary of that one. Yeah, so, yeah, and what we could do here now is sort of like go through that process in the code. Any questions before we go into some more code? Question over there? Ah. That's an interesting idea. Yeah, yeah. I haven't done that, and usually the process of training the GPTs is based upon just next token prediction and try all the future tokens. So I don't think that's being done with these models, but you could certainly maybe adapt the thing. I think what I might also do is maybe share the training set that I've got with you, as long as, yeah, there's nods there. Should we have like a little bit, I'll share you my data and the code for preparing it, and we can move towards, you could even sort of like see if you can get your things to tell some not jokes, yeah? Does that sound like fun? All right. Yeah, so, question over there.
I imagine most not jokes are shorter than 64 words.
They are.
Is there like a nice correlation
That is a great question, and I haven't looked for that yet, but we could. Yeah, brilliant. Yeah, okay. So what are I think is at least some people are in the Slack, the tutorial Slack for the PyData London. So what I'm going to do is I will drop my prepare.py script and the not joke data. Don't laugh too hard when you start reading the jokes, and you can sort of pull that in. Who's managed to get the Shakespeare thing to work, by the way? Yeah. Oh, wow. There's an infinite room. So infinite number of monkeys will have a new play by the end of the day. Right. Great. Okay. Yeah. And so let's all do. Feel free to chat. Is anybody particularly stuck with getting the Shakespeare thing working still, or are we all okay? Wow. It's got a question. MFU. I think that's to do with like how much it's using the CPU. But I might. Does anybody know what MFU stands for? No, I think ask ChatGPT probably is the way to go there. So, anyway, I'm just going to put this mic down momentarily and get you the bits that you would need to start training some jokes. Woo! And feel free to talk amongst yourselves. Compare notes on how the training's going and this and the other. And we'll start again in a couple of minutes. Where's the Slack gone? Oops. Now. I did London. There we go. Okay, tutorials. Oh, that's the wrong thing. That's the wrong thing. How do I reply to my own? Oh, that one. There we go. Right. Let's get not jokes. That's everything. How's the time? 45, halfway through. Okay, so we're halfway through. I hope everybody's got access to the PyData London Slack. And so I'll just let you know, I've put the joke data set is in there. I've put the prepare.py in there. And so if you look, you should have a structure. Let's look like this for your Nano GPT. What have I done? I'm confused now. There we go. So you got a data directory where it had the Shakespeare stuff in it. There's also open web text. If you create a directory called knock and you put prepare.py in there, then and also the knock jokes cleaned thing in there. And I'll just say in advance, I'm sure all of you clever people will discover things that I've done terribly wrong in here. And so, it'll be egg on my face. Anyway, but yeah, in principle, you can then, you would be able to run Python knock / prepare.py, and it will generate the necessary components for you. Was that someone actually laughing at one of the knock jokes? Maybe not. No, something completely unrelated. Yeah. Okay. And then I also do have as well, if you manage to train a model, I've got a knock-knock testing file, which I'll add as well. And that, like, basically you can run and it will assess your model and to see if it can produce knock-knock jokes.
How long should the training process take? I think you have a GPU, but it's not an A100. It's like an 8 gig NVIDIA.
Yeah.
It's been going for about 40 minutes since we started.
And that's on the Shakespeare one, is it?
That's on the Shakespeare.
Okay. Yeah. Give me just 1 sec. I'm just going to get this file over and then we'll. A second. Come on, brain. Reveal and finder. Yes, that's the tip. Yeah, so there was a question there about how long it should take to train. And I think it's going to, your mileage will vary a lot depending on your laptop. So I found, this is an M1, and I feel like the Shakespeare thing trained in about 10 minutes. But my knock-knock thing was taking a bit longer. It was much faster on my M2. And then there are all sorts of different settings. Like I think if you're on an Apple Silicon, there's like an MPS setting that you might want to use. What I would recommend is asking one of the latest models, give it your laptop specs, and ask it about, and just see if there's a tweak that you can do. Cool. Yeah, no, fair enough.
It looks like it's 85%.
Oh, okay. Yeah. Again, depending upon your individual laptop and so on. Yeah, good. Well, I've set it at MP. I don't pretend to be like an expert on these things. I followed the instruction to set it to MPS, and so maybe that was on using the GPU. I'm not sure. Anybody stuck on anything? Any questions? Yeah, go ahead.
I had a question on the embedding, input embedding activations.
Oh yeah.
Your block size is 64, right? So that's kind of like your window for your attention.
Yes.
What happens, when you're on token number 1 or 2 or anything up to 63?
Yes.
What's the deal with not having 64 tokens to your backlog?
So the question there is about the, this is a block size. So during the training, you've got like these effectively 64 tokens coming through, and it's just trying to like predict the next token in each case. So I'm not sure how you.
If I just put in 1 token,
Oh yes.
then how does it?
Okay.
Does it fill up the 63 slots?
Yeah, so that's really interesting because it's like so there's these 2 phases. There's a training phase and then there's sort of like a query phase. And during the query phase, you put in 1 token, and effectively it won't have the rest of those tokens. That block size sort of becomes irrelevant in the query point. And so I'll show in a minute what it ends up doing. The probe sentence that I usually use is knock who's there's Bob, so it's 5 long. And then basically it will do the whole thing for just like a 5, as if the block size was 5, and then use that to work out the next token. And then having got the 6th token, you then do it again with a 6 by 6, again, and then going up until you get an end of token. So
it just kind of truncates that.
It's almost like the whole architecture is able to work with a matrix of an arbitrary length, and it just like you can. So if we just talk through the, we've got this, got the prepare.py file, which is just for tokenizing. There's then I'll go over here. Yeah, so I've got here, I think this is the first, this one here, this file here, this knocks, these config files, which specify what's going on. And so this was the first one that I trained with the kind of distilled GPT architecture, was the first thing that I got actually telling knock jokes. And so you can see here, I think that the block size during training is 64, but that is only during training. And when you probe it later on, and that's what I've got the knock test. And so that one, somewhere in here, it's got Bob, isn't it? Where's Bob? Oh, okay, yeah. So this one is like, it's basically got a series of probes based on these common words. Yeah. And those will go through. We could step through on the debugger. Anyway, I'm conscious of time because it says it waits for no man. Let's try and do a forward pass here. And maybe we'll go. I mean, I don't know how familiar people are with debugging. I think one of the lovely things about having the NanoGPT up and running And what I find at the moment is, you can do it as part of training or what have you, but you can basically, so I think, what did we, sorry, I'm getting lost. Where are we up to? Yeah, so we talked through this, class GPT here is setting up, right, this is a PyTorch network of this structure. And then you've got these forward methods, yeah? And so the forward method, which you'll find, so we've got GPT there, it's got in it, that's that code, other bits and pieces. But yeah, so we've got the forward, so you can see actually that I'm in VS Code here, I can set a breakpoint, and I can stop the code at that point, and I can go and inspect all the values and see exactly what's going on, which is fun. I guess we'll just talk about, so this is again in the model.py. So yeah, so now this is for, I think there's as well as the block size, there's in the batch size. So we might take a block of 64 tokens, right? But then we might have 16 of those, right? So that's gonna, so let's say that the block size 64, that has like 4 jokes in it, right? It's then gonna take 16 times 64, and it's gonna sort of run this all through in parallel. And this is one of the big things with this whole architecture, is what they worked out is that the actual attention framework, it's very parallelizable. So it can take massive advantage of the parallelizability of the GPUs. And so that batch size, you can train big blocks of text multiple times over and get lots of efficiency savings. But yeah, so we've got the module. So now we have this forward method. So there's this process of, you've put some data in, you've said like, well, we've got, during training, it's gonna be these big batches of words. During like sort of test, at the very end when we probe it, it's just gonna be like 5 or 6 words at a time, whatever it happens to be. But so the forward method gets called. There's this device thing for like, that's gonna be CPU, GPU, MPS, what it happens to be. And then we're gonna get the size of the incoming elements. This is always really slow because there's multiple things here. So like, this bit looks really complicated, this first bit with pos. It's basically just getting a list of numbers. I'll show you. Let's go in here and there. And if I run, now I've got to run it on the debugger. So let's find not test, run that on the debugger, debug the Python file, and it will just land on there, hopefully. Think about it for a moment. Talk amongst yourselves. You know I'm not working to the live demos every time. Okay, why has that not worked? Knock test. Was I not pointing at the right thing? That one. Will that now work? Please work. Yay! Worked. Okay. So carry that on. Okay. So there we go. Basically, I'm running my little knock test thing, which is like doing a probe with like knock who's there, banana or what have you. And so now we've like actually hit on this forward bit, and it's got this like pos torch arrange 0 type. Looks really complicated. Looks really complicated. Let's have a look what pos is when that comes through. Pos is in fact, it's a series of numbers, 0, 1, 2, 3, 4, right? All of that effort, right, for just 0, 1, 2, 3, 4. That's why we're sending it five words, right? And this is the position encoding. Is now just going to be just for those 5 words. So if we were doing it with the block of 64, you'd have this would be 0 to 64. But here in this case, we're just doing the 0 to 5. Debugger. So I spent, you have no idea how long I spent getting these arrows to point in the right place. But so here, once we've got that position there, then we're kind of like forwarding to the GPT model itself. And so now we set up that embedding, right? And that IDX there, let's go and have a look at that. It's really nice. I want to kind of stay in that mode there, but then also go to the debugger at the same time. Not perfect, but let's see. Let's have a look at what IDX is. Like so. So you can see here, this is our IDX. That's our representation of the, so this is going to be like knock, who's there, banana, right? And these are the 4, 2, 2, 3. These are our tokens, right, in our 10,000 word vocabulary. And then now we're going to put this through the token embedding there. So then we're going to get out a token embedding. I always do that. Press tab. It's not tab. What does it have to press to make that work? Good Lord. Underscore. Embedding. There we go. So this is what I've spent quite a lot of time over. So now what we've got here, we've got our, these numbers here, these are, they correspond to what we've got here, yeah? So these are now of the 36 dimensions that we've got, this is how active each one of them are, right? So you can see how, this is a representation of, in terms of the original words. And then we've got 5 of them, because there's 5 words. Simples, okay. Bum, 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 bum. And so we do the same thing again for the positional embedding, and then we combine them together, yeah? And so now that X that we have there, that corresponds to this view, like so. We've now got our combined token and positional embeddings, and it's ready to go into the transformer and be transformed, which is of course what ultimately we all want. We want to be transformed into happy, free people. At least that's my plan. Anyway, I'm massively running out of time. Are you gonna, come on, you want to? Come on. Oh gosh, what have I done? Okay, all right, yeah. So we've already talked about this in terms of the structure. Now we're actually flowing data forward through the system. And these end up being the sizes of the matrices that are going through with these batches of 16 times 64 times these 36 representation. In the one I'm doing there from knock test, it's 5 times 36 because it's just the probe, but during training, 16 times 46. There we go, do that. There we go. So then that is the block, like so. Then and finally that you all of these elements within the code correspond directly to this in the diagram. So I think with the right diagram, you can work it out there. Yeah, and then the final stage is there, like the linear and softmax and so on. We take it back through, okay, into which word is going to come next. So if we dive into the block, again, all this code is in model.py. I encourage you to get open model.py on NanoGPT. So within the block, it consists of this. We talked about the GPT-2. They have the normalization, which is basically making sure that the weights don't activations don't get too high. The normalization there. Then we've got this special, I've called it multi-headed attention in the diagram as Vaswani. It's called causal self-attention there, same thing. Then another normalization layer. Yep. And then finally this MLP standing for multi-layer perceptron, which is this big feed-forward layer that sort of, a lot of people when they're explaining how LLMs work, there's a big focus on the attention and how, you work out which words correspond to which other words in the sentence. But a lot of the heavy lifting is actually being done by this feed-forward layer. And I haven't worked out what's going on there, but Anthropic have done some great research, which I'll show you a bit of it. Yeah, okay, so that has not come out in the right order, but, oh, really? What's happened to that one? Annoying. Why is that not all visible at the same time? Let's maybe just stay with that one. Okay, so, okay, I think we're gonna have to do another hands in the air waving thing. I can sense the energy getting lower. Let's do hands in the air. Hands in the air, go on, yay, wave your hands, yay, fun, PyData, yay. Oh yes, okay. So, but what's happened? So I guess, what time? We've got like half an hour. I'm just trying to leave an extra 10 minutes at the end. So we've got 20 minutes. I'm gonna try and get into the details here. But so, what's going on inside this transformer block? This is where the magic happens, right? I mean, the embeddings and so on to create the representation of the words are doing a lot of the work getting it into that space. But then, right, what's happening internally? So people have probably seen these sorts of attention diagrams about what comes out, kind of internally within the attention, which is basically we're taking these, representations of the sentence, let's say, knock knock, who's there, Bob, knock knock, who's there, Bob, and we're kind of working out to what extent these things are connected. And, you get these colored diagrams showing, and this one showing us that the highest value, is that Bob and there are connected. And, the systems are using that sort of information to work out about structures of the sentences. So there was then these further diagrams in the Vaswani paper about how it happens internally. So that block up here, this multi-headed attention, right? That's this, okay? And then inside that, you've got this scaled product attention there, right? And so I was like, no, the diagram's the wrong way around. So I had to invert them. What have I got here? With this one, this is just showing that, yeah, you can see within the code, again, this is in model.py, you can see all of the elements, you've got the normalization layer, you've got the attention, normalization layer, you've got the feed forward step there. Yeah, and with some effort, I managed to flip these diagrams here. So you've got a number of things going on in here. One thing is you've got this multi-headed attention. So the original distilled GPT-2 architecture has, I think, 12 heads in it. And so like you've almost got these like a series of, we've already converted the data from a word representation into this kind of embedding representation. And then we've got a series of further re-representations. And then there's like, 12, at least in that architecture, 12 different kinds. And the way that it's talked about is that's giving you different perspectives. It's almost like you've got a sort of like a mixture of experts. Each of these different heads might be interpreting the data in a slightly different way, and then all of their different ideas are going to be like converted back together. But there's more weights in here, so like parameters that are tuned and trained. You end up with these linear transformations for each of Q, K, and V. So remember how we were talking about the embedding being all the different words and having all the different numbers coming in. So we've got that sort of going on again with Q, K, and V, which stands for query, key, and value. And then I've got, surprise, surprise, more diagrams of images to show you how that all works. What have I done there? That all gets. I want to show you those diagrams. I'm running out of time. What I'm going to do is I'm going to go to those diagrams because I think they're more fun. So let's find this. Don't need that anymore. We don't have positional one. Don't need that. Aha. Is that the right thing? No. Oh, I opened it down here. Okay, yes. This is it. Right? So this is now, see this, I just got this from Gemini 2.5. By the way, Claude got really stuck on some of these things. Gemini 2.5 Pro. I mean, I generally like Google, think you're playing catch up. Gemini 2.5 Pro, pretty good. Question?
Yeah, you mentioned that the heavy lifting is done in the feed-forward neural network within there. Now you say that there are also learnable parameters within the attention network.
Yes.
Could you give us some insights on how all this results during training? What is the effect having more learnable parameters in the feed-forward block or in the attention mechanism, the multi-attention block?
Yeah.
The other way around. Can you give us some insights on that?
I think I can, and I'll end up referring you to the Anthropic people have shown a lot of that, but we'll come to that. It's a great question. What I'll just show you here is, like, so there are these learnable parameters inside the attention mechanism, and that's giving us these, now, it's difficult to say, we've got, again, this is started from those mixed token positional embeddings, and what we've done is, we've said, right, let's recombine those to different degrees, right? So we've now got, like for the query key, this new dimension 0, right? That is a combination to different degrees, right, of all of the different other dimensions. So we get this, re-representation. Now this is effectively here would be, like one word, like I guess this is like the top level. It's not representing a particular word. This is just the representation of the numbers inside. So you get that for Q, K, and V, and they're all slightly different. And then that's like one head. So one head would have these 3 different representations, and then the next head would have another 3, and the next head would have another 3, and so on and so forth. And I'm tempted to go straight to what I've just got here from Gemini 2.5 Pro, which is now, okay, this is now taking, I'm not sure if this is correct because I got it so recently, but so you end up with, a different representation. Yeah, you see, so we've got, this is like the input for knock there, and then it's going into query, key, and value. I don't think this can be absolutely correct, but there's basically a process whereby these Q, K, and V get combined and become another one. I don't think it's done perfectly well there. It's very, very recent. But let's go in here, and we can see. Yeah, let's try and do. Oh, we've got about 15 minutes left before we go to big questions at the end. So we're talking about this multi-head attention. More water. Yeah, so we're going to calculate these. Oh, question?
Do you have like an intuition for QK and V? How should we think about it?
Well, I think it's on the next slide, and I will do my best on the next slide. I guess this one, just overview, as you see in the code, again, Q, K, and V are being split out there. Yeah, so we've got each of these, but basically these are these linear layers with the parameters. And then, there we go, why is it so slow there? Right, this bit we'll get into more detail in the next slide. Sorry, well, let's just get into it. Here we go. Yeah, so this is what I sort of showed already. Well, what we get to, this is a Q, K, and V, right? This is how they get combined. So you initially have Q and K, and this Q and K is sort of created to create the attention, doing a math multiplication on a sort of scale. So like initially, Q and K are trying to give you like the extent to which each word is positioned relative to the other. And to be honest, I really don't understand why we need the V. At the moment, it just is beyond me, I'm afraid. But we can see, there we go, this all being very slow. I just wanted to show you the mapping. It's funny, like it's so much faster when I'm not plugged into the big thing. But so you can see here, like that ultimately here, this is the core of the attention mechanism. In that Q at K, that is us multiplying those two matrices together, that then gets us that sort of diagram of which word is more strongly related to which word. And I guess the best intuition I can give there about what it's doing is it's sort of preparing for when we're going to predict the next word, right? What influences should there be on that? So like if you've got knock knock, who's there, Bob, and then it's going to be Bob who, clearly the biggest influence should come from Bob, right? And then if you're doing that thing, knock knock, who's there, Bob who, there should be an influence from who's to who, and so on. So it's sort of like providing you with a structure to say, okay, which words should be inputting into like the words that come next. But so you can see this is like the very internals of it. So we're going through there, all of those elements comes out like so. And then, you end up with the outputs, and you've got to reassemble them all back together. There's a lot of like kind of like averaging and so on's going on. You've got these, add and norm, if you can see in the diagram here, you see how it comes through, and you have your multi-head attention, right? So you do all this effort to get like an output that's going to be kind of like indicating the influence of the different words on each other in the sentence. And then you take the original incoming data as well, and you merge it in again, and then you normalize it again. It seems to, there's this repeated sort of, so that the add thing is, we're adding in this additional information. Apparently the key that a lot of the work that I've done on this is just looking at one layer, but actually to get it to produce something as complex as a knock-knock joke, you need these multiple layers over and over again. Apparently what this add is about preserving the original information across the layers, and helps with the gradient. Then we've got the normalization, stabilizing things, helping with the training, and so on. So then finally there's this feed forward section. So there's an extent to which the attention mechanism is all about working out which words should influence each other in the sentence. I can't recommend enough the work that Anthropic have done. So if you just search for Anthropic circuits paper, they've done this whole biology of LLMs, and they've really focused on the feed-forward networks. And so they've got these amazing interactive diagrams, and what they've shown, why has that disappeared? That is very strange. Could you please not do that? Good Lord. Okay. Right. Yeah, so this is their thing there. But what this is doing is that they're showing how there are effectively these networks of activation through the layers. So, when I was training my initial version of this with the not jokes, and I had a single layer, it couldn't produce anything more than like repeating a single word, right? But so these, if you see there is this digital analytics group, and then say D, say A, what they've found through their analysis is that within the multiple layers, as you go up in the layers, you get more and more complex representations of things. So they have like here, and they found a node which is like saying this particular example is about turning the name of an organization into an acronym, right? They've got lots of extraordinary examples with like rhyming poetry, working out state capitals, where they've created a sparse representation of the multiple layers there and show how effectively, there's this very distributed representation with different elements of the sort of words coming through and then turning on and off different complex representations going further and further up to work out also. In this case, you can see it sort of going through like these different elements that would imply that it should be spitting out these particular letters, which all then come together in the say DAG. And the big insight for me in the last month or two is right, it's like you absolutely have to have these layers, and your ability to sort of like kind of handle complex representations and sort of like refer to different bits within the whole sentence, you need more and more layers to do that better and better. And they say in their research that this is all stuff on the feed forward, they're not looking at the attention mechanism. So clearly what happens in these systems is the combination of this, these multi-layers in the feed forward section that represent, more complex semantic and syntactic categories comes together with the attention mechanism, which allows it to specify where it should be looking in the sentence for those things. And when that all comes together correctly and it's all been trained correctly on the right kind of data set with the best kind of people, you get the amazing output that we're all seeing from the LLMs. Yeah. So actually, maybe I'm going to come in on time. There's this, I guess in my dreams, I had imagined that we would all go on this journey together and we would like actually be able to go see that representation flow fully all the way through the system. We'd be able to hook it on the debugger and look at. I have spent quite a lot of time on my own. We can, we could, and maybe come and see me afterwards. We can look at it. You can kind of go and see the evolving numbers through every stage in the system, and you can check the matrix multiplication. I've created a Excel version. I've got Excel GPT, right, to visualize all of these things. So this is, you've got here, knock, who's there, Bob, right? These are the values of the input tokens. Got my linear queue there, and I'm basically using Excel, right? So all of the matrix multiplications go through. So, we've got all these different representations with which we're trying to understand it, right? So I've got the diagram, right, from Vaswani. I've got the code itself, right? I've got my different visualizations, and then, but ultimately it's coming down to matrix algebra, right? So I got, this was, for a simple one, it only had not 36, but like a 4 element, and it's just a single layer. But you can see here, like linear Q, linear K, linear V, these all get, and then I end up with my attention scores, right? This is for this sentence, right? Which words relate to each other, right? And then I've got the whole thing going through, like layers of softmax, so it is some, and so on. In other tabs here, I've got these are the feed-forward networks, all of the other bits, and so on. And all of this comes out, and you can see here it's predicting the next word there. It's all just algebra multiplying these numbers together. Extraordinary. Okay, yeah, so let's just go through my last few slides. So once we've gone through this and then, as multiple loops through the block, we end up with this, the linear layer that maps us back to, we've had this representation which has been like some number of dimensions, 36, 128, whatever they happen to be. We're then going to compute, a value for each token in the vocabulary, and then work out, what should come next. And finally, there's this sort of process of softmax. So we've got these logits, which are not quite probabilities, and but using softmax, we ensure that they're, basically all going to sum to 1. They're all going to be, all going to be positive, and that gives us a probability distribution over the vocabulary. So remember, we've got 8,836 words, and we're getting, and then there's, on top of everything else, there's these different selections. So you've probably played with like temperature and top P and top K and so on. There's all these different options. There's different selection modes that can produce different levels, but they're all sort of playing around with the basic set of probabilities about what the next token should be. We can then make a prediction about the next word. It all relies on the backpropagation. I mentioned that before. I haven't got time to go into that today. But yeah, let me show you, as the piece there is, the knock jokes generated. Should we see if they're funny for different things? So as I said, I find it works 100% of the time for this distilled GPT-2 setup, where we had 768 dimensions and 12 heads working in parallel. I think it works. the 36 was the smallest I could get before it just completely fell apart and was not telling knock-knock jokes at all. Yeah, so I don't know, has anybody managed to start training with the knock-knock jokes on their own computers? One person over there? Yeah? Anybody completed the training of the knock-knock jokes? Did it tell a joke? Have you tried it with, yeah, well, in fact, rather than me, I've been speaking this whole time. Sir, did you get a joke from the knock-knock one? What did it say? Drum roll. You're gonna post it into the chat. Yeah. Anybody who manages to get it to tell a joke, do post that into the chat. Let me go here. I was running on the debugger, wasn't I? So I could just carry on, and that will, if we just turn off the debug breakpoints, it should come out. I forget which one I was running. Let's go here. There we go. So this is running like with the 36. So we can see. Let's see the jokes that it got. My assessment here, when it comes down to this, like only 36 embedding we got there. So knock knock. Let's see what works. Knock knock. Who's there? Cat. Cat who? Cat on the air. Well, yeah, ha, 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 ha. There you go. I mean, it is technically a knock-knock joke. There you go. I'll just show you here. If I run this, yeah, I think I've got that there. If I run this with the larger, so this is again just, I found that the attention heads didn't really seem to make much difference. Like if I had 12 or I had 1, the embedding dimension seemed to be the key thing here. So they're 8 out of 10 here. So we've got like this like, knock-knock, who's there? Book. Book who? Book on out. Again, not technically funny, but I defy you. It is a knock-knock joke according to syntactic definition. There you go. So, I think that brings us, actually, God, am I going to be precisely on time, Ian? Ian, just saying hello. I think I've got a clock here. I forgot to wear my watch, but it says, I think I'm going to come in on time. I'm just reaching out to a friendly face because it's been an emotional week. I've been doing so many, by the way, Ian's hackathon hack day yesterday, amazing. Ian's got, check out all of his amazing stuff coming out. Oh, question, yeah, go. Woo, go on. Arguably, I'll be using that in my stand-up later tonight. Oh, you know, these LLMs. They actually, I think it was Salman Rushdie said the other day, right? When the LLMs can be reliably funny, then we've got to start worrying. Yeah. So we're safe for the moment. Okay. Let me put up I've got mine on side, which is, lead into questions. Why is it so slow when I do this? So please also, I've got a podcast, AI Leadership. Woo! Ian's been on it. If you'd like to come and talk to me about AI, come on it. Yay, it's fun. I love talking to people. And read my book. If you are spending a lot of time with computers, it could help. There's other stuff about me. Oh no, good. No. God, what is it? You get all excited with these animation things. What I want there, do that, is also tomorrow at 3:30, I'm running good Lord. Okay. So annoying. Let's do that. There we go. Come to I've got a Python Engineering Excellent Bird of the Feather tomorrow. I also run a Python leadership community. If you'd like to talk about how you get your Python code to be awesome and how to level up your Python skills and all this and that. And what we do in these days when the LLMs seem to be writing some reasonable Python code. That's tomorrow at 3:30. Yes. So isn't it like, our feathered friends and we eat, no. So birds of a feather is the idea, there's a sort of the unconference track that's going on in parallel in PyData. And so what happens there is, we have like a roundtable discussion. So anybody who's interested in coming and talking about, Python excellence in engineering and that stuff and the rise of the LLMs, we've got like half an hour or 45 minutes to chat about that and see if we've got some common themes. And I'll sort of chair that session, but try and get you to do the talking rather than like this, which is a lot of me talking, which I love, but you guys maybe don't know. Anyway, so I think that was my tutorial. I hope that was of some interest. Thank you so much for your kind attention. And any questions? Yes?
Thank you for that talking. It's fascinating. I just wondered, I'd quite like a bit of further time to study the slides. I wonder if you mind sharing the slides.
Sure.
Also, similarly, the code that you used to generate interactive.
Yes. Yeah. So I was hoping in advance of today that I would have the visualization code that you could all run, but I just hadn't got it into like a clean enough working state until just about half an hour before the talk. So, but yes, I'll try and make sure that's all available. Thank you so much. Question there.
Will you make the Excel available?
The Excel? Yeah, sure. I mean, I think, absolutely. The question was, will you make the Excel notebook available? And sure, yep. Yes, question there. Sure. Which was that in the slides or in the? Yeah, I know what you mean. I have all three of them together. Oh, here, yeah, yes, yeah. Yes. 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 Do you want to use the microphone? So, go on.
Okay. I can ask it again.
Please.
For everybody. So as I understand, you were showing that embeddings of the Q, T, and V
Yes.
were different. And as I understand, there were these embeddings were after linear transformation. So it was the same input embedding with positional embedding and normalization. After this is split, transformed by this linear.
Yeah. So we've got.
You get the different embeddings for.
Yes, that's right. So what we've got here is this, and I think actually did I add this? I don't know. But so you've got there's the output, the combined input positional things, and they will go into Q, K, and V, and be transformed. And so you'll have a different. And so if we go to, I think not that diagram, but this diagram, so you've got a different sort of re-representation based on your original of each of those three things, and then that's what's going into this next one here. And then you're doing this multiplication between the two, which sort of creates this, which thing to pay attention to what, and then you've got this. I mean, people have been trying to describe this in terms of, well, by the way, Jay Alamar, I believe, is giving a keynote. He has an amazing set of things in which he describes the way that the query and the key and the value work. I'd refer you to his work for more details there. But sorry, go on. Your question was?
Yes. And that was the first question, so you answered it. And
Yeah.
another one is like you have input attention. It produces like multiple embeddings, and then there is add block, so it just adds these embeddings together.
Yes. Oh yeah, over here, the add here. Yes. Oh, well, this add is like, so you've got they're split into the different heads, and the heads all calculate attention in parallel, and then that gets merged, okay. and then that gets merged again with the original signal from below.
There is concatenation and linear, so it's like, what's the dimensions getting out of the multiplication?
So the dimensions end up being effectively the same. Like you end up with another re-representation of the sentence.
Okay, so it's just adding.
Yeah.
Okay. So I guess that's it.
Yeah. Well, and what I'd really encourage you to do with the Nano GPT is to step through it in the debugger and look at the things as you go through. What I'm hoping, I'll try and release the visualization thing. I'm hoping that we'll be able to get a full visualization of effectively what it is at every stage all the way through.
Okay, I have one more question.
Well, we'll go on. I guess. Unless anybody else, yeah.
Okay, so about the temperature. In the models, there are temperature.
Yes.
I guess I haven't seen anything about temperature. Because it's of the radial search, and this one is just greedy one.
Yeah, so I think the temperature is like at this final stage in terms of after you've got the output probabilities, it's how you select from those probabilities. And I think we can probably see like that will also be in the code. I think if we look for a temp in there, well, I think we've probably configured the temperature. What have I got here in my knock test? Have I got them there? But yeah, that's just there you go, it's a temperature there. So when we're calling this model generate, we're passing in the temperature, top K, and other things telling it about what to grab for. If we just click through, oh, that's the wrong thing. I want to do command click. There we go, generate there. So the temperature is being used there, precisely there. So we've got the logits, which are kind of like the pre-probabilities, and then we're dividing by the temperature. Like influences, like a low temperature means that you'll just kind of go towards the highest probability thing, and high temperatures means there'll be more variation.
So it's like you use radial search here, or? how it's selected, because if it was greedy, it would just select the best one.
Yeah, indeed. But so here, if you see in the knock test thing that I shared, we're using top k equals 40 there. So it's kind of adjusting it to try and give it like, rather than taking the greediest thing, it's giving it a bit of variation to say to select from the top 40. Yeah. So we've got 5 minutes left. I don't know if there's any other questions we want to share with everybody. By the way, I'm available on LinkedIn. Come talk to me afterwards. I love talking to people. Come on my podcast. Listen to my podcast. Spotify, Apple Podcasts. I love talking about this stuff. Yeah. Any other final questions? If not, we can wrap up and really enjoy the rest of the conference. Yeah. Hope to see you tomorrow at the Birds of a Feather Engineering Excellence. Woo.